Number 10, the nitrogen problem. Nobody talks about, everyone who follows. Mars colonization news has heard about the water ice discoveries, the carbon dioxide atmosphere, and the plans to grow food in Martian greenhouses. What almost nobody mentions is that plants do not just need water and carbon dioxide. They need nitrogen, and Mars has almost none of it in a form that living organisms can actually use. Earth's atmosphere is 78% nitrogen. Mars? About 2.6%, and that thin sliver is locked in molecular form that most crops cannot directly absorb. On Earth, nitrogen-fixing bacteria in the soil constantly convert atmospheric nitrogen into ammonia and nitrates that plants can feed on. That entire biological system has to be recreated from scratch on Mars, inside pressurized habitats, with organisms that may behave very differently in Martian gravity and radiation conditions. Scientists have studied nitrogen fixation in controlled environments, but nobody has tested whether the microbial communities that drive this process can sustain themselves across multiple generations in a low-gravity, high-radiation enclosed ecosystem. Without a stable nitrogen cycle, your soil degrades, your crops fail, and your colony starves. There is no current engineering solution that fully addresses this at the scale a permanent colony would require. Number 9, the dust that gets into everything. Martian dust is not like the dust you wipe off your furniture. The particles are incredibly fine, sometimes measuring just a few microns across, and they carry a static electric charge that makes them cling aggressively to every surface they contact. Solar panels lose efficiency within days during dust storms. Spacesuits, if exposed repeatedly, could see their seals and joints degrade far faster than engineers currently plan for. The 2018 global dust storm that killed the Opportunity rover lasted for months and reduced sunlight to almost nothing across the entire planet. But here is what rarely gets mentioned in the promotional materials. Martian dust contains perchlorates, highly reactive chemical compounds, that are toxic to human thyroid function. These perchlorates are distributed widely across the Martian surface, and any dust that finds its way inside a habitat becomes a long-term health hazard. Short missions might manage this risk, but a colony operating for decades? The cumulative exposure from even small quantities of infiltrating dust could cause serious hormonal and metabolic disorders in settlers over time. There's ongoing research into perchlorate-resistant crop varieties and decontamination protocols, but nothing close to a fully proven long-term solution exists yet. Number 8, rocket fuel at scale, is not a small problem. The concept of in-situ resource utilization, making rocket fuel on Mars using local materials, is often presented as essentially solved. Elon Musk has talked about it. NASA has discussed it. The MOXIE experiment on the Perseverance rover demonstrated that you can produce oxygen from Martian carbon dioxide. People nod along as if the hard part is done. It is not. MOXIE produced oxygen at a rate equivalent to what a small dog breathes. Scaling that technology to produce enough liquid oxygen and methane to fuel a fully loaded Starship for the return journey to Earth requires producing hundreds of metric tons of propellant. That demands enormous amounts of electrical power, which on Mars means either a very large nuclear reactor or a solar array covering potentially hectares of surface area, all of which has to survive dust storms and temperature swings from plus 20 degrees Celsius in the afternoon to minus 80 at night. The chemical engineering challenges of running industrial-scale cryogenic propellant production in that environment, with a crew that cannot simply call in specialized repair technicians, represent one of the largest unsolved operational challenges in the entire colonization concept. Number 7, the 26-month window. And what it does to your mind, Earth and Mars align in a way that allows relatively efficient travel only once every approximately 26 months. Miss that window and you are stuck for over 2 years. This is understood in aerospace circles, but its psychological implications for colonists are barely discussed in public conversations about Mars settlement. Imagine you develop a serious medical condition, or a close family member on Earth dies, or the colony experiences a structural failure that makes the habitat genuinely dangerous. You cannot leave. You simply cannot. This constraint imposes a type of psychological pressure that has no real precedent in human history. Antarctic overwinter teams experience isolation, but they know a plane can reach them in an emergency if conditions allow. Mars colonists have no such option. Research on long-duration isolation, including NASA-funded analog studies in places like Hawaii and Antarctica, shows measurable cognitive decline, interpersonal conflict escalation, and, in some cases, serious psychiatric episodes in groups confined for extended periods. A Mars colony would need to manage these dynamics, not for 6 months or a year, but potentially across multiple consecutive 26-month cycles with no guaranteed evacuation option. The psychiatric and social engineering challenges here are genuinely unsolved. Number 6, Martian gravity is not zero-G, but it might be just as dangerous. A lot of space medicine research focuses on microgravity because we have astronauts on the International Space Station. We know what weightlessness does to the human body over months. bone density loss, muscle atrophy, fluid shifts, vision problems. We have protocols for this. Mars has about 38% of Earth's gravity. That is not zero, but here's the problem. We have almost no data on whether that level of gravity is enough for long-term human health. Animal studies in partial gravity environments are extremely limited. We do not know if human bones stabilize at 38% gravity or continue to slowly deteriorate. We do not know if children conceived and born on Mars would develop normally, or whether their skeletal and cardiovascular systems would grow in ways that would make returning to Earth physically impossible or even medically dangerous. This is not a fringe concern. It is a recognized gap in the scientific literature that researchers have flagged repeatedly, and there is simply no ethical way to get the data we need without actually putting humans on Mars long term. We are planning a multi-generational colony based on a fundamental unknown about whether human bodies can sustain themselves in that gravitational environment. Number 5. The magnetic field problem is worse than you have heard. Mars lost its global magnetic field billions of years ago when its molten core cooled and solidified. Earth's magnetic field deflects the solar wind and shields us from a constant bombardment of charged particles and cosmic radiation. Without it, the Martian surface receives radiation doses that NASA estimates would exceed acceptable limits for career astronauts within a relatively short surface stay. But what happens over decades? The math gets genuinely alarming. The annual radiation dose on the Martian surface is estimated at around 230 to 300 millisieverts per year, compared to about 2.4 millisieverts as the average annual dose for a person living on Earth. Long-term colonists living on the surface would face dramatically elevated cancer risks, potential damage to the central nervous system, and reproductive health complications. Proposals to solve this include building habitats underground, using water walls as shielding, or constructing massive bermed structures covered in meters of Martian regolith. All of these work to varying degrees, but none of them have been engineered and tested at livable scale. You also cannot shield the entire surface, meaning any activity outside, farming, construction, repairs, comes with radiation costs that accumulate relentlessly across a lifetime of Mars residency. Number 4. Who actually owns what you dig up? The legal framework governing Mars is genuinely chaotic, and this will become a critical problem the moment a colony starts extracting resources in any meaningful quantity. The 1967 Outer Space Treaty, which most spacefaring nations have signed, states that no nation can claim sovereignty over celestial bodies, but it says almost nothing clear about resource extraction by private entities. The United States passed the Commercial Space Launch Competitiveness Act in 2015, effectively telling American companies that they can own resources they extract from space bodies, even if they cannot claim the territory itself. Luxembourg passed similar legislation. Other countries have not, and several space law scholars argue these national laws directly contradict the spirit, if not the letter of international treaty obligations. Now imagine a Mars colony backed by a private company that has spent hundreds of billions of dollars getting there. They start mining water ice, extracting metals, and processing regolith. Another nation's colony arrives and claims the same resource deposits. There is no Mars court. There is no enforcement mechanism. There is no agreed international framework for resolving this conflict. The legal vacuum is not a detail to be worked out later. It is a potential source of catastrophic, colony-threatening disputes that nobody in the mainstream Mars conversation seems particularly eager to confront. Number 3. Communication delays. Make Earth useless in a crisis at minimum. A signal from Mars takes about 3 minutes to reach Earth. At maximum orbital separation, that delay stretches beyond 24 minutes each way. Real-time communication is impossible. This is known. What is less discussed is what this actually means operationally for a colony facing an acute emergency. A habitat pressure loss. A medical emergency requiring surgical intervention. A cascading systems failure. All of these demand immediate decisions. The colony must be entirely self-sufficient in its decision-making capacity, with expertise available on site for every possible crisis category. That means the crew needs to include or be trained to the level of structural engineers, surgeons, chemists, geologists, psychologists, electricians, and mechanical engineers simultaneously. The cognitive and knowledge demands placed on a small colony population are extraordinary. Current thinking suggests AI systems and detailed decision tree protocols could fill some of these gaps. But relying on autonomous AI systems to guide life or death medical procedures or structural repairs in an environment where every mistake could be fatal represents a level of technological trust we have never actually validated in practice. Number 2, contamination. Goes both ways on the rules. Our unclear planetary protection is a field of study dedicated to preventing biological contamination between Earth and other worlds. Forward contamination means Earth microbes reaching Mars. Backward contamination means potential Martian biological material, if any exists, reaching Earth. The scientific community takes this seriously. The public generally does not know it exists. Here is where it gets complicated for colonization specifically. A permanent human colony is, by definition, a massive source of biological contamination. Humans shed millions of microbes per hour. No sterilization protocol can make a human crew biologically inert. The moment you commit to a permanent colony, you are committing to permanently and irreversibly altering the biological state of Mars. If microbial life exists in subsurface water reservoirs or in protected geochemical niches, a human colony almost certainly contaminates those environments before we even discover them. We could be destroying evidence of extraterrestrial life, or an entirely separate branch of biology, without even knowing it. The scientific and ethical stakes here are enormous, and the policy frameworks governing them are, at best, works in progress that have not kept pace with the speed of Mars mission planning. Number 1, Mars might make you permanently unable to return to Earth. This is the problem. That sits quietly in the background of every long-duration Mars mission concept and almost never gets named directly in public. Extended life in lower gravity, higher radiation, an enclosed habitat with recycled air and a radically different microbiome, and the psychological adaptation to a completely alien world, could produce physical and neurological changes in long-term colonists that make returning to Earth as environment physiologically dangerous or impossible. Returning from Mars after years of living there means surviving a months-long transit, then re-entering Earth's full gravitational pull with a body that may have substantially adapted to 38% gravity. Cardiovascular systems that have adjusted, bones that have remodeled, neural pathways that have reorganized around a different sensory and gravitational environment. Earth could, for the first generation of true Mars settlers, become an unreachable destination, not because of launch windows or rocket fuel, but because their own biology has diverged from the baseline requirements for life on this planet. This means colonization, once begun in earnest, may be a genuinely one-way biological commitment, not just a logistical one that changes everything about the ethics, the recruitment, and the long-term governance of a Mars settlement, and it is a conversation that is barely happening in public spaces where these plans are being promoted. If you want to keep diving into the science that does not make it into the headlines, subscribe, and we will keep bringing you what actually matters.